Hi, my name is Ulises Martin, PhD student at the University of Akron. Today, I'm going to talk about the study of the passive film of 316 Ln stainless steel rebars in synthetic concrete pore solution under stress corrosion cracking. For today's presentation, I will briefly introduce the stress corrosion cracking or reinforced concrete, materials and techniques used in this study, results and discussion, and end on conclusions. Stress corrosion cracking is a natural phenomenon which occurs whenever three conditions are given. First, we need a material susceptible to corrosion. We need an aggressive environment, and we also need a tensile stress. Stress corrosion cracking is extremely dangerous, as it won't show any previous sign to failure. A case of stress corrosion cracking failure was the Genova Bridge in Italy, where 43 people died as it collapsed in 2018. To study the passive film of 316 under stress corrosion cracking, saturated calcium hydroxide plus calcium chloride solution was done to simulate the concrete. The mechanical setting included a slow strain rate technique, while electrochemical monitoring of the passive film was done by electrochemical setting. The mechanical electrochemical standard can be seen above. First, we have here the current and stress transient, where at the beginning we have a decrease in the current density, meaning that our passive film is being formed. However, some metastable pitting is seen as we get close to the yield. Whenever we change from the elastic to the plastic region, we have a sudden increase of the current, reaching the 100 micron per centimeter square, where the passive film breaks and we have the passivity breakdown. After that, we have a sudden decrease of the current density, followed by some metastable pitting where our passive film tries to recover. However, because of all the damage taken by the current and also by the higher stresses, it's not able. That's why we see a continuing increase of the current density till we get to the UTS, where again passivity breakdown occurs and we have a constant current density showing the dissolution of a rebar. Similar results were seen by the Nyquist plots, where we have an improvement from the preload to the 80% of the yield. Once we cross the yield, we have a decrease, followed by the 90% of the UTS, where we have an improvement. However, it's not even close to the preload values we had before. After that, 100% of the UTS and the failure are even lower, showing even lower corrosion properties. All the data where we had a passive film was fitted with electric equivalent circuit A. We have two time constant. However, when passivity breakdown occur, we change to the second one, B, where the time constant of film changed to be a warp element, showing the oxygen diffusion. This was seen on the boat plot of such Nyquist diagrams with a tilted angle at 45. Grammar chronings were also done to show the robustness of the data. Finally, we studied semiconductive properties of our passive film by the Mott-Schottky plots, where the M1 represents the formation of chromium oxides and M2 the formation of iron oxides, which are not as protective. With increasing stress, M1 and M2 tend to flatten, showing an increased amount of defects on our passive film. With these values of M1 and M2, we calculate the carrier density, where the Nd represents the donors, made out of the iron oxides, and the acceptor of the chromium. As we see that the Nd is higher than the Na, we have a more doped passive film, meaning that we have more unstable and hence more prone to corrosion. As a conclusion, we saw that the passivity breakdown occurred whenever we cross from the elastic to the plastic region, as well as whenever we were close to the UTS. The increase of oxygen diffusion seen by the warper was seen whenever the passivity breakdown occurred, changing our reaction kinetics from charge transfer to mass transfer. Thank you.